Okay, let's take a look at this next worksheet here. It's kind of the natural progression of work and energy. Work net equals F net times dot delta R, which equals change in kinetic energy or negative change in delta U, right? So what ends up happening here is we can treat this as a differential equation, which we did on the other worksheet, right? We said work equals the integral of F net with respect to R. Now the dot product's still there. This still has to be the component parallel to the displacement vector, right? Or, you know, you'd have to do this three-dimensionally if it was a function that was multi-dimensional, but we never have that. So we never really need to worry about the vector here because it's always a function that is in one single direction at a time. So really, we really can just think of this work equals integral of force with respect to position. We really don't need the vector notation there because it's always in one single direction for our purposes. And it really doesn't get until you get into upper level physics that you need to factor in multi-directions. All right? All right. From there, right, we had kind of alluded to the idea that, well, if area under force versus distance gives us change in energy, right, then really also the derivative of energy with respect to position, you know, notice we're using x here, right, so I guess I'll keep that x, should give us force, right? It should go both ways. Take the derivative of energy or work, you get to force, you take the integral of force, you get back up to work, right? So I have some graphs trying to show this. Now the weird thing here is they never give us the derivative of work with respect to position. They always give, it's always a potential energy function that they give us, not a work function. So remember, we've talked about this before, change in potential energy is equal to the negative of the work, or I should say the work is equal to the negative of the change in potential energy. And we've talked about this in class, talked about this in the previous video. So when we get this equation, this is what it ends up looking like. Force equals the negative derivative of energy with respect to position. Why wouldn't we just keep it like this, dw dx or dk dx? Well, it's just, we're usually given potential energy functions, not work or kinetic energy functions. I don't know why, we just typically aren't. We think about potential energy as existing when an object is in a field. An object is placed in a field. So work isn't done until that field moves the object. So I guess that's probably why we're given the potential energy function. It's more like the energy available in a field at a certain location. By a field, I mean a force field, like gravitational field, electric field, and so on. So, you know, that's really the reason why we're probably given potential energy. So just a couple functions that we kind of already know about here, right? We know about gravitational potential energy. It goes up as the height increases, right? So that's the potential energy. The derivative of that, the negative derivative of that with respect to position, which would be du dh, negative, ends up being negative mg, so the force is negative. Pretty cool. It's the same thing with elastic potential, right? 1/2 kx squared, right? If that's our potential energy function, the derivative of that ends up being negative kx, right? So if it's, you know, if it's a positive x, it's a negative force. If it's a negative x, it's a positive force. And you think about this as an object tied to the end of a spring, right? So if the object's in a positive location, the spring force is in the negative direction. The negative sign does matter. It tells us it's a restorative force, right? You can read about that here because it'll always try to bring it back towards the center. Now, from there, we just kind of start looking at some of these functions. So this is one of the very first examples. I'm not going to write up the whole solutions now, but you know, we'll take a look at this. So Object located in a potential energy field, described by the equation below. U equals negative 4x squared plus 4. Sketch quantitative potential energy versus position and force versus position graphs for the function over an interval of negative 1 to positive 1. All right, negative 1 to positive 1. So let's just kind of think about it. So at 0, U is going to be positive 4. So I'm going to, right, at x equals 0, U is positive 4. X equals 1, it would be 1 squared, all right. It would be negative 4 plus 4 would actually be 0. And then at negative 1, because it's squared, it's also 0, right? And the potential energy here, so this is meters, this is joules, ends up looking like this, right? Ends up looking like this. It's a curved function, so it's probably going to look like that. Now, what does the force versus position graph look like? All right, so let's go ahead and figure out the forces. Force equals negative du dx. So the force is going to be negative 8x. Negative 8x. So the y-intercept is 0, so at 0 it's 0, so plus 1, negative 1. At positive 1, our force would be negative 8. All right? At negative 1, our force would be positive 8. Negative 8 newtons. And we have positive 8 newtons. This is x in meters. All right, so we have a nice, I guess I didn't do a good job plotting that point. We have a nice linear line. All right. What would happen to an object released initially at rest at a position of 0 meters? All right. What would happen to an object released initially at rest at a position of 0 meters? All right. So, if it was released at rest at 0 meters, what's the force at 0 meters? It's nothing, right? So really nothing would happen. There's no force. Force at x equals 0.0 meters. From there, now what would happen is given initial velocity positive 2 meters per second at the origin. All right, so if you give it a little perturbation, if you knock it off, right, that potential energy gets really, goes really steep down towards 0, right? The force gets really, really negative as you give it a little push to the right. Now, wait a minute here, hold on a second. All right. Oops. Oh, I messed up the force versus time graph. Oh, Harmon. See, I always do that. It's negative of negative 8x, so it's positive. I'm looking at this like, wait a minute, this isn't right. I'm sorry. Jeez. My bad. Sign error. Double negative. Classic. I always forget that with that. That's a really annoying thing. Doesn't change the answer to part B, right? Nothing. There's no force at x equals 0. What if now after your initial kinetic? Because I was thinking here, wait a minute. If you give this a push, this thing's going to go flying away really fast, right? It's just going to rapidly give up that potential energy and get kinetic energy. All right? So that force, right? You give a little push to the right, that force is going to increase to the right, and it's going to go flying away. All right? So that's my fault. Sorry about that. It's going to go flying away at a high speed. So it would start moving to the right and accelerate at a rapid rate. Right? It would actually, the force increases. The force increases. At a rapid rate. I'm done giving it. Determine how much total mechanical energy there would be. So, EMEC, all right, is always the sum of the kinetic and the potential. All right, so if we know the velocity at a particular location, and we know the potential energy at a particular location, we can figure out the E mechanical. So you got to use the initial velocity given. So this is continuation of part C. So if I can find the total energy at the origin when it's launched, I can figure out the mechanical energy at any other later point in time. So this would be 1/2 of 1 kilogram times 2.0 meters per second squared. And I have to find the corresponding potential energy when it's at that velocity. So that would be the potential energy when it's at the origin. Okay, that would be potential energy when it's at the origin. And when it's at the origin at 0 meters, its potential energy is positive 4 joules. So you just have to continue this calculation. It's 4, 1/2 of 4, ends up being a total of 6 joules of mechanical energy. So that's cool. Initially, if it had no velocity, its total mechanical energy would be 4 joules. But since I gave it a little initial velocity, it also has that. So 2 joules plus 4 joules, 6 joules. So now, at any time later, it has to have that same amount of total energy, right? So to determine the speed of the object once it reaches 1 meter, well, let's see what's the EMEC is always 6 joules. So 6 joules has to be equal to the K at positive 1 plus the U at positive 1. It has to be equal to that total the whole time. So 6 joules kinetic energy is, well, that's what we're looking for. And what's the U at positive 1? Well, it's 0, right? So that 6 joules at a location of positive 1 is all kinetic energy. It's all 1/2 of 1 kilogram times v squared. And this is the big picture for these types of problems, is this potential energy graph. What you're doing is you're figuring out the total energy. So if you know the location and you know the velocity at a particular location, you can figure out how much total energy the object has. And then you can use that to figure out its speed anywhere else. For instance, if it was at 0.5, I could plug in 0.5 for potential energy, right? And that'd be how much potential energy I have. And then I could solve for the kinetic energy, because I know the total has to be 6. And I can find V. So V equals 2 times 6 square root. V equals square root of 12. Oops. V would be 3.5 meters per second. All right? Very cool. Like that one. Number 2, just a different energy function, right? U equals 6x to the 4th, so you can plot that, right? You can plot that. See what that looks like in your calculator. It's always useful to think about that, right? This is a little different one here, right? So at x equals 0, it's going to be 0. At x equals 1, it would be 6. At x equals negative 1, it'd also be 6, right? And it's going to be a pretty sharp curve, right? It doesn't tell us to plot it, but it always helps. Now, what's interesting about this one, if you look at the force versus time graph for this, it's going to be negative 24x cubed. It's kind of a funny thing. But because it's negative, the force, it's always going to be negative. The force is negative 24 x cubed. You know, no matter, so if x is positive, this is going to come out to be positive. The force is going to be negative. If x is negative, this is going to come out to be negative, and the force is going to be positive. This is one of those situations where it's a restorative force, right? And when you have this shape, you know, if you give it a push, it's like pushing something uphill. The potential energy goes up. It's always going to want to come back down. It's always going to come back down. All right, so if it's released at 0, again, nothing would happen, right? If you give it a little push to the right, the force is going to bring it back. All right, the force is going to bring it back. All right, give it a push to the right, the force is going to be to the left, it's going to pull it backwards. And it actually would oscillate back and forth, this object. This one here, what initial speed would the object have to be pushed in order to reach a position of x equals 2 meters? Well, if it makes it out to x equals 2 meters, that means that it would come to a rest at 2 meters and then get pulled back towards the center, right? So if it's going to make it out to 2 meters, we need to find the u at 2 meters. All right, and that's 6 times 2 to the 4th. All right, 6 times 2 to the 4th equals 96 joules. All right, so if it's going to make it out to 96 joules, that's how much potential energy it's going to have. You can think about the bar graph. So it's going to end up with 96 joules of potential energy when you push it out that way. So that means you need to give 96 joules of Ke initially. All right? You need to give 96 joules of kinetic energy initially. So 96 joules equals 1/2 mv initial squared. All right, so 2 times 96 divided by 0.5 equals v. And that's v equals 20 meters per second. All right? Very cool. Very cool. So you could have to shoot it out at 20 meters per second. It would get out, it would lose that 96 joules of kinetic energy. Remember, this is something moving in a straight line, you know, because it's only x, right? So you'd shoot it out with 96 joules of kinetic energy. It would slow down pretty quickly, get turned around, and come back. And at the middle again, it would have that 96 joules of energy at the beginning, kinetic energy, but it'd be moving to the left, right? So now it's going to go to the left, going to be pulled back towards the center, going to go back, and as long as there's no dissipated force, this thing's going to oscillate. This thing's going to oscillate back and forth. Very cool. Harmonic oscillator, you would call this. Determine the magnitude direction of the force acting on the particle when it reaches 2.0 meters. So F, I already found the derivative, is negative du dx, which is negative 24 times x to the third. 6 times 4 is 24. Any of you still say that in your head sometimes? Don't be embarrassed. Negative 24 times 2 to the 3. Maybe you never learned that little rhythm to figure that out. 192 newtons. Okay, 192 newtons, and actually I forgot the negative sign because it's trying to play back to the left. Magnitude and direction. So as long as you put the negative sign, you're good to go. Now, the AP Physics C practice problems, good stuff. Nonlinear spring, compressed, all right. You know, just shown below. Assume the magnitude of the force applied by the rings follows this form, right? Which quantity should be graphed in order to yield a straight line. All right, so if you want to yield y equals mx plus b, which is a straight line, you have to use x squared. So you're going to have to plot x squared there. All right, and we'll see what you can do with this problem eventually here. This one here is a little different, giving you potential energy function. Sketch u versus x, so you just plug in numbers, every digit maybe, and see what you get. Put it in there. Force is the derivative of this. All right. There's a substitution here possibly. You guys need to figure that out, or a quotient rule of derivatives. You've never done that in physics, but it does exist sometimes. Suppose that the object is released from rest. Determine the speed of particle at x equals 2 meters. So again, this is what we just did in that previous worksheet. And then you have a lab question, which we'll talk about in class. So that gets you set up for worksheet 2. Pretty much you've gone through this. You've got to do the last couple questions. We'll be good to go.